Thank you, John. Technically, my job title is Technical Consulting Engineer, and I'm the lead for the Advisor XE product line as well as the Inspector XE product line. And in fact, before I took that position, I worked as an engineer on both of those products. So I know a little bit about what's going on under the covers and a little bit about what they do from the surface, and we're going to talk a little bit today about Advisor XE. So today we're going to do a presentation. It's mostly going to be kind of an overview, and some of you have seen some of this material before. We're going to talk about what Advisor is, why a tool like Advisor can be helpful, and get a little bit into the nitty-gritty of how you use it. And after that, I'm going to bring up a demonstration. I'm going to show a couple of our sample codes. I'm going to actually look at the suitability pane that you get when you're running them, and give us a chance to play around with some of the advanced modeling tools that you can't really see very well when you're sitting looking at a slide. And after that, we should have plenty of time for questions and answers. Make sure you write in your checkbox in your little box and let John know if I'm talking too fast. Sometimes I have a problem with that. So what is an Advisor XE? So Advisor XE is a tool that helps you model parallelism. Helps you add annotations to your code to introduce parallelism. Adding parallelism is important to take full advantage of modern processors. Almost no one is sitting out there with a single core processor anymore, so you really want to be able to take advantage of all the computation power you've paid for. But that can be very difficult. So Advisor is a tool that's going to help you step by step go through the process of modeling what happens if you parallelize particular sections of your code. We give you a nice GUI. We give you a nice step-by-step analysis system. What we don't actually do is auto-parallelize your code. Auto-parallelization has been the holy grail of compilers for a very long time, and it's just much more complicated than anybody anticipated it was going to be. So we don't actually parallelize your code for you, but we will help you find the right places in your code to try parallelism and tell you whether or not you can just naively parallelize this section and some hints to make sure you get going properly. And after we've done that, we don't actually modify your code for you. We allow you to do that yourself. We do that for a couple of reasons. First of all, we don't know what exactly is going on in the rest of your code and the rest of your domain. You may have particular reasons that you want to choose TBV versus Silk versus native threads as your parallelism paradigm. So we're going to let you pick that out for yourself once you're done. Here's just a few things you might want to know about the tool, where it works, when it works. We have a GUI that integrates with Visual Studio on the Windows side, everything from 2010 to 2013. We have a standalone GUI available on both Windows and Linux platforms, and we have a full-featured command line interface available on both sides. We support Microsoft compilers, Intel compilers, and GCC, or any compiler that uses GCC semantics. We work on various versions of Windows and Windows Server, as well as several popular distributions of Linux. At this point in time, it doesn't work on Android or Mac OSs. We work with C, C++, C#, and Fortran programs. So there's really only a couple of questions you have to ask yourself if you're trying to decide whether to parallelize your code in general. And the first question has to be, is it safe? If I parallelize this portion of my code, am I going to get what I expect? Am I going to have data races? Am I going to have deadlocks? Am I going to accidentally change the results? Is it safe for me to make this parallelization here? And second of all, is it profitable? Am I going to get enough speed up from doing this work to parallelize this code to make it worth the overhead of doing it? And the answer to that is not always yes, because sometimes the overhead inherent in taking a complicated functionality and splitting it off into threads isn't going to be worth the effort, especially if you can only really split it onto a couple of threads. So if the answer to both these questions is yes, then it's pretty obvious you should do it, presuming, of course, you have the manpower resources to do it. But figuring out when the answer is yes is not always easy. And it's particularly not necessarily easy if you don't have a lot of background in working with parallel code. So the idea of Advisor is to really give you a tool to help you answer these questions for yourself. So what are some of the advantages of using a tool versus just jumping in and trying to do this naively? There's some advantages. We allow you to model your code while it's still serial. So you aren't going to fail due to bugs you've put in when you've guessed about parallel execution. It's still executing in serial. We're just figuring out what would happen if you executed it in parallel. You can experiment with several things before you commit to a specific implementation. You look at different loops in your code that you want to parallelize before deciding which ones you want to move forward with. You can also, give it a try with TBB and then give it a try with OpenMP and try out different things. And all of your test suites should still pass when validating the correctness. You don't have to worry that while you're working on this, it will invalidate your test suites. They'll all work as well. Another advantage of Advisor XE over some other tools to help you parallelize your code is that it works on your code even if your code is already partially parallelized. We aren't going to get hung up on finding loops that are already parallel. We'll just go through and show you what you've got in your current status and work from there. We can also, by modeling, help you avoid some of the major mistakes. We will help you measure performance and make sure that you're focusing in on hotspots. As we all know from Amdahl's law, if it isn't expensive, it isn't going to do us very much good to parallelize it. We can help you predict how well things will scale. We'll help you predict what kind of benefits you're going to be able to get from running your parallelized code. We can give you some information about whether you're getting a good load balance or whether you're now having threads that are going to last for a long time and really short threads, so by the time you bring it all together, you're not really gaining that much. And we can tell you how much overhead you're costing yourself by going to this model. The automated analysis makes it much easier to catch cases that people miss, particularly if there's little corner cases, often code that's nowhere near in proximity to the code that you're changing. Sometimes it can be really hard for somebody who isn't completely familiar with the code base to know when they're giving themselves problems. So it's a good idea to have an automated tool that will, by its nature, look out there and find those weird corner cases. Making good decisions early saves you a lot of time. Having to make changes to your code and then roll them back can be a nightmare. And basically, Advisor XE will help you increase your return on investment for parallelization. The idea is that you won't have to invest quite so much work before you can get useful benefit out of it. One of the most useful things you can look at when you're working through Advisor is what we call the workflow, which takes you through step by step what you should do to try to add parallelism to your code. And the graphic on the side is actually what it looks like when you have it opened inside of Visual Studio. But the first step is that you're going to do survey tools to figure out where are the right places to add parallelism. What are the most expensive parts of my code that I might want to think about parallelizing? You're going to add annotations, which will help you experiment with turning these things into parallel code without having to go in really deep and climb through the structure. We've got a suitability tool that says, okay, if I parallelize those, how much benefit could I get? And it'll also allow you how much benefit will I get if I change some of the factors about it. And we're going to talk a lot more about that later. There's a correctness tool you run then, which will help you to find potential synchronization problems. If you aren't careful, it's really easy to give yourself races. And so we'll make sure that we let you know if there's a race or if there's a problem. And while we don't tell you exactly what to do about it, we'll give you some good hints about things you might want to try. And then after that, we'll give you some assistance to convert from those annotations to a parallel framework of your choice. You'll have to do the work, but we'll give you good help about exactly what kind of things you can insert instead of the annotations to make it work. So the first thing you're going to have to do if you're going to run Advisor is you're going to have to set up a project. And if you've ever used any of the Parallel Studio components from Intel, they pretty much all have this kind of project set up. From here, you're going to say which application you want to run, if there's any parameters you want to pass, where you want the output, things like that. Another important thing to consider here is that if you look up above, there's things for binary and symbol search and source search. When parts of this analysis are best done on a release build and parts of this analysis are best done on a debug build, because some of these things you're going to want to actually get back into the source code and you're going to need to get the symbols back out, which means that if you are keeping your symbols in a non-standard location, you need to make sure you add them here. If you're keeping your source in a non-standard location, you need to add it here. If we can't resolve the symbols, we'll give you information about the modules, but that's not nearly as helpful. Once you've done that, I would recommend going ahead and opening that workflow pane that I showed you earlier. We're currently going through a change in how we show that on the dashboard, so I went ahead and clipped a couple different versions so you could see it. So when you look at this, you see that there's a specific button to open the advisor workflow, but then there's also individual buttons if you just want to run a particular analysis. But basically, these are the buttons that will help you open the workflow, and from then on out, I go through the workflow. And as many times as I've used this tool, it's easier to me just to open the workflow and work it through that way. Plus, I also frequently go back and look at old analyses, and I find it easier to just go through the workflow for that. The first thing you do is you push that button and you run the survey. When you run the survey, it essentially does a hotspots analysis to tell you what parts in your code are the most expensive. And when the survey pane comes up, it looks kind of like this. And what it is showing you is you have your choice of a bottom-up or a top-down view of the various calls in your code and how much of the time when you were running was spent in that particular call. So right here, you can see what portions of the loop were pretty much just overhead as it went into the next section of the code, and then when it started actually taking some time to do the work. Often when I do this, what I will do is I will go right back to the summary pane, which is one over. The summary pane sort of collects up all the information about all of the tests that you've already run on this code. So in this case, since all I've run is the survey, what it has here for me is information about what were the top time-consuming loops and what were the details about this collection. I find this very useful because if you look at this, you can see that there are two particular calls in the code that took up the most time. And in fact, you can even tell that they're nested because the total time for those two calls is substantially more than the entire collection time. So I know that if I'm going to get a lot of use out of parallelizing this code, that's where I need to start. That if I get that down to a good parallelization, I might want to move on and look at intersect objects and the other things and see if there's anything I can do there. But I'm likely to get the most bang for my buck towards seeing what I can do inside of Tachyon serial CPP, which isn't real surprising given the name of the file. So after I've figured that out, the next thing I have to do is go in and annotate my sources. So advisor annotations are all available to you. They're part of the install. They're shipped in a header file. Annotations are little macros so that you can easily turn them on and off. We didn't want to make them something complicated. We didn't want to make something that changed the shape of your code. You just insert these into your code. You can comment them. You can if-def them. You can do whatever. They're just little tiny macros. And they tell the analysis code about what sections you intend to investigate further for parallelization. There are probably 100 of them. You will probably never need to use anything more than the short list I have here on this slide. Over the next few slides, I'm going to give you examples in different programming languages of annotations and give you a chance to see how they work. And we're going to start off with, this is actually the code that is used in some of our samples. And if you look at it here, this is a C++ example, you'll see that basically what we do is that we decide this is the section of the code that I want to try to parallelize. And you bracket that with a site begin and a site end. And then inside that site, you specify a task.
Should I do it
and
again?
The task, what? And the task is basically, this is the chunk of information that you wish, or the chunk of code rather, that you want a particular thread to run. So in this case, we're saying, okay, this loop here, the larger of the two for loops, this is what I want to parallelize. And in order to do that, I'm going to take each of these things between task begin and task end and give it to a particular thread to run. The string that is inside the task begin, the task end, and at the beginning of the thing, that's actually just a label so that when you get your data later, if you annotate more than one site, you can tell which site's being talked about. So that's really just a string you use to keep track of it for yourself. This is a much simpler example, but I wanted to make sure that I gave you a chance to see what the annotations look like in Fortran as well. So this is just a little code fragment. But again, you see that you call the site begin before the loop that you want to parallelize, and you cancel it afterwards, and then inside the loop you indicate that this is the task you want to send out to an individual thread. And it's the same on C#. The actual semantics of the call to site begin and site end change with the language, but the general layout is pretty much exactly the same. These examples, as well as many other examples of annotations, can be found inside the help. So I want to make it clear that I know having to put annotations into your code to get data can be annoying, but there are lots of examples and lots of samples, and it isn't that hard to at least make the first pass on annotating your code. Once you've annotated your code, you want to find out, the whole reason of doing this was to find out whether or not the code in this particular range that you'd like to parallelize is in fact scalable, whether you're going to get any benefit or enough benefit out of parallelizing this section for real. In a perfect world, obviously, you'd like to get linear scalability. It would be wonderful if every time you ran 2 threads, it ran exactly twice as fast. But unfortunately, there's several things that can block scalability. Here it mentions data sharing, but there's also can frequently be problems with just the overhead of splitting off particular tasks into multiple threads can sometimes be painful. Sometimes in order to avoid data sharing, you're going to have to set up many additional, essentially local variables and then combine them again later. And that can get kind of expensive depending on the kind of application you have. So there are things that will stop scalability, so you want to know whether or not it actually really scales before you go any further. And to determine that, we run suitability modeling. This is actually a screenshot, and this is actually one of the 2 samples I'm going to show you later when we're demonstrating, of the tachyon rendering code after we've done suitability analysis in Advisor. And what I want you to notice right now is mostly this graph. So the graph tells you whether you're scaling well, whether you're scaling some, or whether you're not scaling at all. And the sort of target on it tells you, this is how many cores you've told me you've got. This is how much scaling I think you can get if you take these annotations and turn it into a parallel area. So there's a lot of information here, but since this is the kind of code it has a lot of scaling. And I wanted to show you, so I have a second example here. This is the N-Queen sample, which again we'll look at later. This problem is essentially only has 14 threads worth of work. So it's never going to scale to more than 14 threads, no matter how many cores you have for it to run on. So you want to be able to see that too. We'll go into a lot of the other details of what you see in the screen when we go to the demo, but I wanted to show you that. What you can't see in these screenshots, because there's just too much information on the screen, is that underneath this graph there's another section where we talk about specific problems that may have caused it not to scale. So for instance, in the example being shown here on the right, there was a load imbalance. Some of the threads were being forced to carry much more work than others, and so they didn't get done at the same time. And you don't get perfect scaling if some of your threads take longer than others. And this example also had a fair amount of runtime overhead. It was kind of hard to get the tasks split out properly. So these are the kind of things that can inhibit your scaling, and these are the kind of things that we want to warn you about, and frequently we will have suggestions about things that you can do to try to reduce these. So you've done this, you've done your suitability analysis, and so now you have an idea of whether or not you might want to consider moving forward with this parallel region. The next thing to do is to check correctness, because so far we've done nothing to make sure that you didn't violate the program's behavior by changing it to a parallel program. So you want to run a correctness analysis. Until we got to correctness analysis, all the stuff we've done before could be done on a release build, should be done on a release build, because you want to know what is slowing me down in my real code and what is going to scale well in my real code. So all of the analysis we've talked for so far, you would want to do on a release build. The correctness analysis you actually want to do on a debug build, because it's important not to lose some of the things that the compiler optimizes away if we're actually going to make sure we find all of the dependencies, and if we're going to be able to give you good information about where in the stack you are. So correctness analysis you'll actually want to run on a debug build. Now, for all of these analyses, you don't necessarily have to scale it to 1 million to do the testing. You can run a small data set, and as long as it's representative for your survey analysis and for your scalability analysis, you get decent data. And I'll show you with the demonstration how you change once you have it to model if you had larger tasks or more tasks. For correctness, you have to make sure that your loop is running at least a couple of times so that you have enough information there to see what would happen multiple threads. But other than that, you can always go to a smaller test case. It just has to run through all the code. It doesn't have to run through all the code to the full extent with a large data set. And because it's using binary instrumentation and because it has to run on the debug build, the correctness analysis can take a certain amount of time. So it's sometimes very useful to make sure that you use a smaller data set and you do less frequent loops when you're doing correctness checking. But if you want to run it just the way it is, that's fine. You can run it just the way it is. Because what we're looking for here is problems. You're not really looking to see how fast. Fast doesn't matter. You just want to know what problems. And if you're looking at what we have here, you can see that in this tachyon sample, we actually have a problem with memory reuse. There is memory that's being written to every single time through the loop that is not in any way protected. And so we have a data race here, and we're not going to get the right answer out of our code. So once we see that, there's actually annotations that you can use to mark things that need to be fixed for correctness. Now, sometimes you can just basically lift out the variable. Sometimes you can just take what was a global variable and make it into a local variable, and that will take care of your problem. But sometimes you're actually going to need to put in locks. And so we have additional annotations which you can put in at this point to say, don't worry about this one. Pretend I had a lock on it. Of course, that means that when you do convert your code to be actual parallel code, you will need to put some sort of synchronization on that variable. But for right now, you can just annotate it because we don't want to go through all the hassle of figuring out which is the best thing for this situation. We just want to tell it, if I put this lock here, what's that going to cost me? Once you've done this, you'll probably need to rerun suitability because it is completely possible, depending on the code, that if you put in enough locks to avoid the correctness issues, you may lose the value of parallelizing. It may cost you so much on lock overhead that it's not worth it, or it's certainly not the best thing to try right now. So once you've done this, you kind of need to rerun suitability. After you've done this, you can go back to the summary page, and you'll see all the information that you've gathered. So you'll know what you've run. You'll know if there's any correctness problems left you haven't dealt with. You'll know what things were taking you the longest amount of time. You'll know how much gain you could possibly get from running this. And if I could scan down in the middle of a slide, the collection details would tell you the length of all these collections and what kind of time bounds there were, and also details about what kind of system you were running it in and everything else. So once you're done, you have all the information you need in order to decide whether to move forward with turning this into a parallel region of code right here on the screen in front of you. And what we can see right here, since actually this was run before I fixed the correctness problems, you can see that if fixing the correctness problems was free, that we would get almost an 8x speed up for this part of the code, which would give us almost a 3x speed up for the code as a whole. So now you know that this is something that you want to convert to parallel. How are you going to do it? And the answer is that although we won't put it in your code and we won't make the choices for you, and your organization may have preferences about what they use for parallelization, you may have something you're more familiar with, there are a lot of factors that can go into that decision. But we do try to have very clear examples inside of our help about what, if you have this, write that. And we have that for TBB, for OpenMP, for Silk Plus, and for native threads on Windows and Linux. So you have the ability to say, okay, I want to use TBB. What does it look like? And we'll show you what it looks like. I also wanted to mention real quick before we go, before we go on to the demo, that we do have a command line interface that will do all of these things. Obviously, a lot of things are a lot harder to see in a flat text report than they would be in a GUI, but they're still available to you. So for collection, it's just a simple collect and what you want, and report, it's a report and report out what you want. And I've written down just one brief example here This particular one says collect survey data. It says that I want the project information stored in /adv. It has information about search directories, but most of this is not required. You could write this very simply just by having the collect survey and the name of the application and run, and you'd be done with it. There's lots of information about the command line interface available in the online help. And if you have any questions about that, you can be sure you can contact me afterwards. I'll let you know more. And I think, in summary, so there's a tool to assist in the parallelization of serial code. It'll help you find the code that takes the most time, model the available speed up, find the correctness errors. And we do this with just a lightweight annotation system, so you don't have to go in and make a lot of permanent changes just to find out what's going to happen. And that is the summary of that. But before we go on to questions, let's go ahead and let me show you some of how suitability actually works in the wild. So John, please let me know if this isn't easy to see on the webinar.
No, it looks like it's fine.
Okay. So what you're looking at now is a live Visual Studio 2010 integration of the Current Advisor product. I ran it myself a couple days ago. This is our Tachyon sample that ships with the product. Tachyon is a rendering software, and so as you might expect, the critical loop is in fact in the rendering portion, and it's pretty much embarrassingly parallel. So right now we're talking about if we were doing this on a CPU. If you look at this target system, it's a drop-down box, and you also have the option of seeing what your scaling would look like on Xeon Phi or if you were offloading to Xeon Phi. To make it a little clearer, you could run this native on the CPU, you could run this native on Xeon Phi, or you could do most of your work on Xeon and then offload the interesting bits to Xeon Phi. If you click on one of these others, it will instantly change the graph. It's a very quick little modeling algorithm, and let you know whether or not this is actually appropriate for Xeon Phi, because that can be somewhat of a difficult thing to figure out. So we wanted to make sure that the tool would specifically tell you this. And then we can go back to our CPU. Actually, offloading, I believe, for this one is exactly the same. That's right. Because so much of this is bound up in the code that you actually want to run parallel, it really doesn't make any difference whether you go offload or whether you go native. We also give you the opportunity to choose a threading model here. Now, you haven't actually put the threading model into your code. This is just changing the model to reflect how much benefit it thinks you could get from different versions of it. So this is a simple enough example that it doesn't make a lot of difference which threading model you use. But right now, if you look over here in the maximum program gain, you can see that we're gaining about 2.97, and there's some serial and predicted time here. Go away. But if I change it to be, say, Silk Plus, you'll see it does make some difference to the serial time and the predicted parallel time. And I think if I drop down to native threads, it actually makes enough of a difference that the gain for sites drops, but it's 0.01x. So it's not crucial. But you can see that we're actually modeling what would happen with different threading models. Another thing that we have over here is a CPU count. This doesn't make a lot of difference, but it helps you change what you see in the graph so you focus in on the right thing. So you can choose to model it as if you had 8 CPUs or 256 CPUs or whatever you actually had available to you. And it mostly just changes the graph a little bit, makes it a little bit obvious where on the curve you are. So that's sort of what's going on in the top. In this box up here, there's only one thing annotated in this code, so right now I only have one annotation site showing. If I had gone through and annotated several things in my code, I could go from line to line to line and see what was going on at each annotation site. Likewise, if I click on site details here, I could see information about each site and each task within the site right here. Now there's information about particular instances. So you can see I went through that site once and there were 512 tasks in it. And you can also see the difference between the maximum and the minimum instance time, because in real code frequently it doesn't cost the same amount every time you pass through a loop. In this case, some portions of the frame you have to render are a lot less expensive than others. So this can give you some information about that. I'm going to go ahead and make this bottom window a little bigger. So right now, we're running at the default for this test, which is, it takes 0.06 seconds per task iteration, and we're running 512 tasks. And when I do that, I can see that right now, load imbalance is costing me 1.58%. If I made the tasks substantially smaller, if I said, you know what, I'm going to break this up, I'm going to make my tasks really, really small, and I apply that, that will actually change the graph. So now what's happened is that I'm actually only scaling up to about 8. And the reason that the mark is here and then the bar is there is that there's a difference between what you might maximally get and what we think you're going to get because of the different iterations. So we're going to give you a little bit of information about that. It's almost like a little error bar on the top. And when you do this, you see that I'm now paying quite the heavy price because of load imbalance between the tasks. Because they take just such a little period of time that the difference between them is really costing me a lot. And again, and over here in the runtime modeling section, you can see that it's now telling me that if I did something to enable task chunking, I could possibly get 1.29 speed up on that. So let's not do that because that looks like a really, really big mistake. So let's take that off. We're going to make sure that the tasks don't actually take that little time. Well, what if we made the tasks take longer? What if we made each chunk that goes to each thread bigger? Again, you can model it and see how that changes it. And in this case, I think it renders our load imbalance trivial. The things are so big that the load imbalance between particular passes is trivial. So that is, I've gone through basically what you have to do that you can do here. I mean, you can also increase the number of iterations through the thing. So I can go down and say, well, what if I only ran 4 tasks? Well, it turns out it only scales to 4 if you run 4 tasks. What if I went up to all the tasks in the world? For this, since this particular code is embarrassingly parallel, you can run any number of tasks and it'll basically remain parallel up to that level of tasks. In fact, if anything, increasing the number of tasks to 125 times the 512 has actually increased our parallelism up here because it is, again, changed the load imbalance. So let's go back to normal just so I know where I am if I come back here. And now let's take a look at a different sample. So this is, again, this is the NQueen's example that shipped with the product. This is the most recent Advisor 2015. It's integrated currently into VS 2010, and I ran this just the other day. In this case, this is a classic program for determining how many of the chess pieces, the queens, can sit on a certain size board without being in danger from one another. So it's blocked inherently by the size of the board in terms of how scalable it will be. The default run for this was a 14 by 14 board, and you'll notice that if you look at the scaling, it turns out it scales more or less exactly to 14. If you increased the number of iterations, which effectively is making the board bigger, turns out it scales up to the size of the board because that's the way it works. If you went to model this on Xeon Phi, you would see that if you were running, 100, this many, it would be useful. But if I take us back to our standard size board, there's no point in running that on a Xeon Phi. There's just not enough parallelism there to really take advantage of it. And I'm sorry that this keeps popping up. So basically, what you can use this to do is you can look at your code and you can run a fairly small sample or a fairly basic sample, and then you can say, okay, I ran it 14 times because we were testing it, but what happens if I scale it way up? Do I still see this kind of scaling? Do I suddenly start costing myself things because I've completely flooded the system and now I'm paying a lot of overhead? Basically, it allows you to come in here and run once. So you just run the code once, and then you get to use the model to see what would happen if you changed it to do different things. And we've only been about 35 minutes, but that is, in fact, the material that I brought to talk about today. So if you have any questions, if there's something else you would like to see.
Do we? We have a few. Yes.
Okay. Well, let's
Yes.
get started then.
Let's get started. Does Advisor work for a module?
Does it work for a single module?
I believe so.
Okay. The answer is, I'm going to make that go away again. The answer is that yes, it will work for a particular module. It will probably show you information about the performance of of all of the modules in your initial analysis when you do survey. But once you've done that, you should find it fairly easy to concentrate on those from a particular module. And it might be reasonable for me to submit a feature request and ask for just a simple way to filter it to a particular module when you're doing survey, so that it's easier for you to see what to move forward with.
Okay, thank you. Next question is, does Advisor support any other virtual machine like Java?
Not at this point in time.
Can you say anything about Advisor and the use with Iris Pro graphics?
I don't actually know anything about Iris Pro graphics. Sorry, so I really don't have anything to say there.
Okay. Next question is, how do I decide the sample interval?
You don't really have to do much to decide the sample interval. We're doing a survey analysis. So I suppose I could go back to my slide and get that thing. Any standard sample interval should do. You don't need to get real detailed. We're not looking down to hardware counts or anything quite that basic. It kind of depends on how deep you're trying to go right now. I mean, the first few times you go to parallelize a code, you're going to want to start with the things that are really the most expensive. So you don't need to go to a very low sampling rate, very high sampling rate rather, because you're going to see it. It's a pretty gross situation. Once you fix the bigger things, you might need to go smaller. But my estimation is that the generic presets are going to be pretty much good for anybody, even doing scientific codes.
Okay, thank you. During suitability analysis, which thread library does it use?
Internally, it doesn't actually use any thread library at all. I mean, it just runs the analysis, and it uses an algorithm and a set of heuristics to determine how scalable particular things are just in a generic. If I could parallelize this, how parallel could I make this safe? Could I make this? The only thing that happens with the threading model in the suitability pane is we apply some factors based on overhead for that model and the kind of code we're looking at to try to determine how that might impact. So the raw run isn't using any threading model at all. It's just running an analysis to determine how parallel it can make things. And after that, everything that's being applied is just a modeling factor.
Okay, thank you. I have multiple test runs. Can I combine them together for survey?
Unfortunately, there isn't really any good way to do that. If your test runs are completely disparate, sort of like unit test runs, then you would probably have to run them sequentially and look at it. If you were going to do that, I would really recommend using the CLI, and then you could combine the reports that way. It wouldn't be the same as being able to see it in the graph, but you could get the reports of what were the most expensive loops and combine it all together and look at it that way first.
Very good, thank you. Does this tool work well on an MPI code? And if so, does it basically tell you, how to do MPI plus threads?
We haven't done a lot of testing with this on MPI. It will work on MPI code in general, I believe, but I mean, that's almost a secondary level of threading. It should be able to tell you of the code that you are running on a particular node how to thread it, yes. But it's not really built to go system-wide across MPI.
Okay. So you had mentioned the CLI. One of the questions is, can the command line interface be scripted?
Absolutely.
And if maybe you could point the person, where would they find information? Is that in the online documentation?
That is available in the online documentation. And actually, I had it up earlier today, but I closed it before I came to this meeting. But yeah, if you open up the online documentation for the tool, maybe it won't actually come up pretty quick. There's a whole section in here on the command line, and it talks about the interface and the syntax, and all the various options are all available in here. And then, of course, if you have any questions, you can always contact us about it as well.
Okay. Next question is, since Advisor already detects the markup entered in the code, why can't it just drop in the TBB replacements when prompted?
We get asked that from time to time, and it's a little bit of a complicated question. Part of it is that we could not reliably guarantee that we wouldn't be dropping in things slightly wrong. Everybody's coding methodology is a little bit different, and it would be too easy for us to make assumptions about how you'd written your code and mess it up. And that's even assuming we knew which paradigm you wanted to use where. I mean, I suppose it would be theoretically possible that we could set up some sort of tool where you say, okay, you've done this, now put it in TBB. But we'd sort of have to make a best guess heuristic at how that would work, and then you would have to test it, because we wouldn't be able to guarantee that we would get it in just the right place. So we wouldn't be able to guarantee that we wouldn't be introducing errors after we went out of our way to help you find all the ones that were there. I know everybody would love it if we could just make it so that you push a button and we figure out the best parts and parallelize the code, but unfortunately the reality is that we really need you to make that last step and put in the final code yourself.
Okay, great, thank you. Next question. If the code is built with Microsoft C++ compiler, can you run Advisor on it?
Yes, you can. We don't actually care which compiler you compiled it with. There's no static analysis portion to this. It's all done dynamically at runtime.
Okay, good. Thank you. There was a question, but there is an option to choose TBB or OpenMP. There's no context. I think it was in reference to something you said. I think the answer is yes with the drop-down.
Yeah, you can choose until TBB from the drop-down, and if that is what you decide to go with, we do have information to help about how to convert from annotations to TBB.
And the same with OpenMP?
And the same with OpenMP. So we have information about TBB, Silk Plus, OpenMP, and also the Microsoft threading library available in the help, and then the Linux threading libraries as well.
Okay. And a follow-on question, it said that it doesn't use the thread library internally, but why are there options to choose? I think this may be poking at how we model how these different parallel solutions work, maybe?
Yeah, it's about how you model it. You can't really see on the samples that I've demonstrated today because these are pretty simple samples, and they were chosen expressly for that purpose when we shipped them with the product. But if you've done any parallelization, you know that there are situations where OpenMP is more powerful than native threads, and where native threads are more powerful than OpenMP. And we take some information about what we saw when we ran the code, which we ran sort of pseudo-serially to find out the data for the suitability, and some information about the threading paradigm you're looking at using, and we use that to make our best modeling estimate of whether that particular model is likely to be particularly effective here. But it's all modeling, it's all heuristic. This is not actually rerunning your code with substituting in TBB or anything like that.
Okay. if it doesn't use any thread library, how does Advisor account for thread creation and deletion latency?
We determine what things you are saying that you have to take into that thread. We're getting kind of into the weeds of suitability here. But we determine what things you are going to have to take from the generic site case and move into that thread. And we do an estimation based on what things you're going to have a copy of for each thread. One of the things that happens when you change the threading model is that these threading models have different costs for generating threads and different startup times and close down times for threads. Likewise, when you put in the annotated threads, there are different kinds of locks that you might use, and those synchronization events and locks have different costs, and you can also model that inside this runtime modeling area over here. So the answer is that we take advantage of what we know about the costs of that particular model and starting and stopping, and what we know about the costs of what's going to have to be duplicated on a per thread basis or copied over to make sure that we have memory available for all threads, and we use that in the estimation.
Okay, thank you. Does Advisor support co-arrays? I'm assuming this is a Fortran question.
Yeah. I believe that Advisor supports Fortran co-arrays, but to be honest, I haven't tried them out.
And kind of a related question. It's just the question was Fortran module.
Again, I'm pretty sure it does. Yeah, I would be very surprised if it didn't, but I haven't actually played with that.
Okay, thank you. Can you apply OpenCL threading model on the serial code?
There's no reason you couldn't. I'm assuming that they mean when they have annotations and they're going to thread it. There's no reason they couldn't. There's no reason that you couldn't use this and then go to one of the threading paradigms that we don't actively talk about here. There is also, provided that it all compiles cleanly beforehand, as far as I know, no reason that you couldn't run Advisor on code that was already partially threaded with something like OpenCL.
Okay. How to disable annotate macros?
You sort of have your choice on how to do that. You can just comment them out. You could set them up under an if-def. It's mostly a matter of we wanted to make them just a simple single-line statement so they were as easy as possible to comment out. So probably most of the time the simplest thing to do is just good old double-slash comments on C++ or the like. If you know you're going to be doing a lot of work in your program, it might be worthwhile setting up some sort of wrapper so that you can just say one time in the program, ignore all of these and have that work out. But for most people, you're working 1 or 2 sites at a time, and it's really a matter of commenting in or out 4 or 5 lines of code at each site.
Okay, thank you. Does it work with Visual Studio Express?
It does not work with Visual Studio Express.
Okay. What about matrix multiplication? A blocking scheme over the nested loops would be ideal. Your examples only illustrate something with inner function. Does Advisor ever recommend blocking?
There is actually a sample that we ship that does a matrix multiply, and we do allow for nested sites and tasks, and that's how we work with the matrix multiply. I don't actually have it up to show right now. But yes, I mean, obviously if you're going to get much parallelism, you're going to have to be able to block and wait and things like that. And that is supported with annotations as well.
Okay, thank you. How well does this tool work with memory-bound codes that are limited by memory bandwidth?
That is actually kind of, obviously we're not built to really understand the memory bandwidth that you have going, and that is sort of the problem. If you're CPU bound, we're going to tell you a lot of information. If you're memory bound, we're not going to tell you as much information. And I'm going to take advantage of this question to briefly mention that we are actually in the process of trying to add some tools for vectorization to Vector Advisor, not for this release, but possibly for a future release. And one of the things that we are also looking into adding, and if we added it for that, we would also add it for this, is the ability to tell you whether or not your computation is actually memory bound, as well as give you information about things like memory stride patterns and access patterns. If you are more interested in that, please feel free to email me, and I will tell you more about it. It's in its very early stages, but we are very aware of the fact that we can really only help you if you're compute bound. If you're memory bound, this isn't going to help.
Okay, thank you. How to start the GUI after using the command line interface to collect a survey?
If you go to your Advisor XE directory, in the bin32 directory, there's an add vi_GUI.exe. You just run that and it'll launch the standalone GUI. Or if you want to use the integrated GUI, you can open the generated result file, and it should open basically a default project and open it for you inside of Visual Studio.
Thank you.
You were kidding about a lot of questions.
Oh my gosh, they're coming in too. We've got some very interested people. How does Advisor account for KMP_affinity?
I don't have a good answer for that. I'm sorry. Why don't you send that one to me, John, and I'll see if I can't get a good answer for that. I think I'm going to have to take that one to the architect, though.
Very good. Thank you. Let's see. When Advisor states max site gain, it assumes all AVX and SSE options are enabled?
It assumes that what is available on a default version of the target is available. You'll notice that in the target system, we just say CPU. We aren't assuming what kind of chip you have. So we don't necessarily assume that you have all of those AVX instructions and whatnot available to you. So this maximum site gain, and plus most of that's about vectorization, this maximum site gain is based on the assumption that you are running sort of a default Xeon.
Okay, and maybe this is a related question. Is Advisor affinity aware? Can you change affinity settings?
No.
Okay. Anything else, or that's it on that?
Unfortunately, I don't have more information on that.
Thank you.
But no, there's no way to set the affinity inside of Advisor.
Okay.
Or to tell it about affinity, I should say.
Okay. Is there a granularity highlighting capability or feature?
No, there is not. And if you want to give us more information on what you're looking for on that, we'd love to see the feature request.
Okay, thank you. Can the tool report cache misses?
This tool is not set up to report cache misses. If that's the kind of information you're looking for, you probably want to be running vTune or Amplifier. And you can run Amplifier either before you get into this. I mean, if you looked at the survey report and you've ever used Amplifier, you can see that that's pretty much the same as hotspots analysis in the Amplifier tool. So if you're interested in finding out about cache misses and things like that, I would start with Amplifier and see where you are before that. And if you think you're having issues afterwards, you could also go back to Amplifier. I do not believe that Amplifier will deal with code that has annotations inside it, so I think unfortunately you'll have to turn off the annotations to do that. But the cache information, that sort of thing, is not really inside of Advisor. That's more an Amplifier thing.
Okay, thank you. Target CPU implies a CPU within the workstation. What about developing on a laptop and targeting a Haswell CPU in a cluster, or am I required to run Advisor on a cluster also?
I ran the thing that you are looking at that I have shown you modeling with the Xeon Phi. This is my laptop, which does not have any Xeon Phi chips. So the where it is being modeled for does not have to be where it was run. But like I said earlier, we don't actually break out particular chips in here, so I cannot, tell you the difference between running this on different levels of Intel chips. The idea is that you will get that gain. That's why we talk about scalability and not straight up performance. So we're telling you it'll run 8 times faster. We're not telling you how much you had before or how much you would have if you were running this on a particular Intel processor. We're just telling you that it will scale to 8 times faster than it was at base.
All right, very good. I think we have time for one more question, and then we'll have to call. And there's a few additional questions that it doesn't look like we'll get to. Can advisor model scheduling? For example, OpenMP can have static schedule, dynamic schedule. Can advisor predict the runtime difference between the different schedules?
The suitability report, which is where that would be if it was anywhere, is not really set up to handle that kind of granularity on its reports. My computer decided I wasn't talking to it enough.